All right, let's jump into the lecture 3 slides. We're going to talk about something called conditional probability as well as something we call independence of events, um, starting with conditional probability. So, the idea behind conditional probability is that um, if we have two events, A and B, um, it might be that if A happens, it changes the probability of B happening, or vice versa. Um, so, given a probability space where we've got sample space, sigma algebra, probability function, and some set or event, remember sets are the same as events, B in our sigma algebra, which has positive probability, we'll see why in a moment. The conditional probability of A given B is defined as this. So the way we interpret this is probability that A happens given that B happens. And so the idea is if I write probability of A, this is, we might call it an unconditional probability. Unconditional probability. So we don't care about the event B if we just write probability of A. Probability of A is just describing the probability that A occurs whether or not B occurs. But this idea of conditional probability is if we know that B occurs, it might change the probability that A occurs. And so we define conditional probability as it's defined in this formula. So probability of A given B is probability of the intersection of A and B over probability of B. So the event we're conditioning on always goes down here in the denominator. Okay, so that's conditional probability. Let's, before we get into some examples of conditional probabilities we might want to compute, let's show that this new function, which takes sets and returns probabilities, let's show that it actually satisfies these Kolmogorov axioms of probability. So the first one is I need to know whether I'm always going to get a non-negative number for any set A in the sigma algebra. So let's see if we will always get a non-negative number. It's defined in this way, and I know that that this probability is always greater than or equal to 0. This one we've assumed is greater than 0 in the definition of conditional probability, and so this is always greater than or equal to 0. So the first axiom of the Kolmogorov axioms is satisfied by this new function which we're calling the conditional probability. The second one is if I put in the entire sample space, will I get 1? That's the second Kolmogorov axiom. So if I put in the whole sample space, I'm going to compute the conditional probability according to its definition like this. And if I take the entire sample space, that's a funny looking omega, if I take the entire sample space and intersect it with the event B, I'm just going to get B. So this on the inside is just B. So I get probability of B over probability of B, which is 1. So we're good. The third one is that countable additivity one. So if I have like A1, A2, and so on from my sigma algebra, which are pairwise disjoint, that means there's no overlaps amongst any of these. I want to check whether n equals 1 up to infinity. I want to check whether this is equal to the sum of these. So remember, this property is called countable additivity. Countable additivity. So is that property satisfied? Does this conditional probability function satisfy this? So we start with the left-hand side. So this conditional probability, by definition, is probability of the intersection between these two events divided by probability of B. If I use the distributive law, I can write this as the union of a bunch of intersections. And once I do that, I can see that I've got the union of a bunch of disjoint sets. So these are all pairwise disjoint because I started with pairwise disjoint sets A. So these sets A and intersect B are also pairwise disjoint. And because I know this original, like, unconditional probability function obeys the third Kolmogorov axiom, I can write this probability of a union as the sum of probabilities. AN over B, probability of B. And I can just rewrite it in this way. Probability of B is down there for every single term in the sum. And so this is like just the probability of AN given B, according to the definition of conditional probability. So we're also happy with the third axiom. Okay, so we've got a legitimate probability function when we choose some event B on which to condition, and then we want to compute these kind of updated probabilities for an event conditional on the event B. Let's just do an example to see how this works. So consider this really simple situation where we roll 2 dice. It has this probability space. Here's the sample space of all the outcomes. The sigma algebra we should use is all subsets of omega, including omega itself. And the way we would compute probabilities is by counting the points in any event and dividing by 36, which is the total number of points in the sample space. Okay, so if we define a few events and then compute conditional probabilities, it would look like this. So I guess first let's just compute the probability of B. The absolute difference in rolls is less than 2. So that would be like all of these ones satisfy it because they're no different. These are different by only 1. These are different by only 1. But all the others are different by 2 or more. So now we just need to count how many there are. So there's 6 there, 5 there, and 5 there. So 16. So this is like 16 over 36. And now probability of A given B. I need to compute this as probability A intersect B divided by probability of B. So A intersect B. A is that we roll doubles. So rolling doubles is all of these. So if I take A intersect B, it's actually just the set A. So I get 6 out of 36 in the numerator. And in the denominator, I have the probability of B, which was this 16 out of 36. The 36's cancel, so I get 6 out of 16. If we look at what we just did, in the second one, I'm conditioning on the event B. Once I'm conditioning on the event B, I can ignore the rest of the sample space and it's like B becomes my new sample space. So if you tell me that B is definitely happening, that is, I'm conditioning on B, then I update my sample space to only B. And so we could compute this a little more quickly by just writing down this conditional probability as the number of events in A and B divided by the number of events in B. So we have 6 here on the diagonal, and then we have 16 events in B, so we can come to it that way too. Okay, what about A union B given C? Okay, the event C is that the sum of the rolls is 10 or more. So let's see how messy I can make this. It looks like that's everything down in this corner is the event C. And so now I want A union B conditional on C. So this is going to be A union B intersects C divided by the probability of C. All right. Probability of C is 1, 2, 3, 4, 5, 6 out of 36. So 6 out of 36 on the bottom. And now I've got A union B intersect C. So my picture is getting really messy now. So let me clean it up a little bit. Okay, here's the event C. And let's see, here was my event B. Let's see, this was all in the event B, and then in the event A, it was like this. So it looks like these events are like A union B intersect C. And there's 4 of those, so 4 out of 36, and so I get 4 out of 6, which is 2/3, if I did all of that right. Okay, so just a very simple visual of conditional probability. I was just double checking that I did this right. I think it's right. Okay. Now, a really important rule that we use a lot to compute conditional probabilities is Bayes' rule, owing to this guy, Thomas Bayes, who lived a long time ago. Here's the idea behind Bayes' rule. Let's say I've got some event B, and then I've got a partition of the sample space consisting of the sets A1, A2, and so on, A6, A7. And the idea is I want to compute the probability of one of these sets in the partition conditioned on the set B. So given that B happens, what is the probability that this certain member of the partition collection happens? And Bayes' rule tells us that, so if I have this partition, which is the A's, and B is any set with positive probability, then I can compute the conditional probability of AI, where this is one of my partition sets, one of the sets of the partition. I can compute this conditional probability with this formula. Okay, so let's figure out why we can do that. If I start by just using the definition of conditional probability, I would put AI intersect B over probability of B. And now we're going to rewrite both the numerator and the denominator to get this expression. This numerator, we're going to we're going to write as probability of B given AI times probability of AI. Why can we do that? It's because the definition of conditional probability gives me that the probability of AI given B is probability of AI intersect B over probability of B. Also, if I want the probability of B conditional on AI, I'm going to get probability of AI intersect B, and I divide this time by AI. So what I see from these formulas is that I can always write the intersection probability, AI intersect B, in a couple of ways. I can write it as, if I use this formula, I can write it as probability of AI given B times probability of B. Or if I use this formula and just move this over to the other side, I can write it as probability of B given AI times probability of AI. So let me write this here. So I'm using this to go from here to here. And that gives me the numerator of Bayes' rule. Now the denominator is just another way of rewriting the probability of B. And I've put here how that's done. Notice that this B, if I wanted to pick the probability of B, I might shade this circle. But it's made up of these different parts. Here's like B intersect A2, here's B intersect A4, here's B intersect A, I guess maybe this was A3, 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 A2. I can write the probability of B as the sum of these different probabilities. So the sum of these probabilities. So I can always write probability of B is the infinite sum of probability of B intersect AN, n going from 1 to infinity. This we learned as the law of total probability. Law of total probability. Okay. So what I can do after that, I should have written this out more neatly. N equals 1 to infinity. B, A, N. What I can do to get to this expression in Bayes' rule is I can write each one of these as probability of B given AN, probability AN. And then it looks like this, except I used a J down here. Okay, so this is sum n1 to infinity, probability of B given AN, probability of AN. Okay, so really Bayes' rule is just rewriting a conditional probability using some facts that we know. I just put probability B there. So this in the denominator is just another way of computing the probability of B. Okay, we'll get to use that in an example here in a minute. A simpler version of Bayes' rule, in the case that that I have only two events in my partition, is what maybe we can call baby Bayes' rule, which uses as the partition A and A complement. So this would be like A1 and this would be like A2, and those are the only two events we have, and those form a partition, so A and A complement. Then we see, like, if I want to compute the probability of A given B, then I have this, and then this sum in the denominator is just a sum over two things, where my first set in the partition is A and the second set is A complement. Okay, so this is the rule we most often use in our introductory statistics classes. Let's use Baby Bayes' rule to do an interesting exercise. So when we think we are sick with something, we can maybe get tested to see if we have an infection. And these tests that we use are never 100% reliable. So if I let I be the presence of an infection, and T is the event that you get a positive test. So, okay, I is infection, like the infection is present, and T is the event that you test positive. These tests that we use have what we call a sensitivity and specificity. So the sensitivity of a test is a conditional probability. It's the conditional probability of testing positive given that the infection is present. We want it to be high, like above 90%. So let's suppose I have a test for some infection which has sensitivity 0.92. And specificity, we also want our test to give us a negative result when the infection is not there. So this conditional probability is the probability you test negative, and you test negative given that you don't have the infection. We want that to be high. Let's suppose it's 0.98. Let's suppose in the setup of this exercise that if you randomly select some individual, they will be infected with probability 0.05. So infection is present in 5% of the population. Then we can use Bayes' rule to compute some kind of interesting probabilities. You as an individual, when you go get tested, are mostly interested in these probabilities. The first is, given that I test positive, so this is probability that you are infected, given you tested positive. And the next one would be probability not infected given that you tested negative. All right, so let's figure them out under these sensitivities and specificities. If my tests were 100% reliable, then these probabilities would be equal to 1, but they're somewhat less than 1 because my tests are not perfect. Okay, so probability that you are infected given that you test positive. I want to use the information given to me. This 5%, this is just probability that anybody's infected. So this is 0.05. That's what that's telling us. Okay, so since I'm given certain conditional probabilities, but I'm interested in these different conditional probabilities, Bayes' rule helps me to flip the conditionality and get what I'm interested in getting. So you can think about using Bayes' rule whenever you want to flip the conditionality. So here we go, using this rule. I want to put in the numerator the probability of testing positive given you're infected times probability infected. Then that same thing goes here again. And now I have probability testing positive given not infected, probability not infected. Okay, let me move this down here. So now I want to plug in what I know. So this guy is 0.92. That's my sensitivity. So this is my sensitivity. And this is the prevalence in the population, 0.05. And so I've got that same thing down here, 0.92 times 0.05. Now let's figure out these ones. probability of testing positive given that you um, don't have the infection. This is going to be like 1 minus the probability of testing negative when you don't have the infection, which is 1 minus, remember this was what we called the specificity of the test, and it's 0.98, this number. So that's going to be 0.02. And then this here is going to be 1 minus probability of the infection, which is 1 minus 0.05. So this is 0.95. So 0.95. Okay, so if you do that, you're going to get 0.7077. And so this is going to be of interest to you because if you test positive, this is how sure you can be that you actually have the infection, given this prevalence in the population and this sensitivity and this specificity. Okay, what about the second one? What's the probability I don't have the infection given that I test negative? This would be relevant to you if you tested negative. Using Bayes' rule, I use the conditional probabilities I have to get the conditional probabilities I don't have. So I'm flipping the conditionality using Bayes' rule. So here I want to put, again, probability test negative, but this time given that I have the infection. So this is just applying that, the baby version of Bayes' rule. Okay, so now I got to put what I know. This is my specificity, so that's 0.98. This is, remember, 0.95, so 95% of the population don't have the infection. And so that goes here again, because that's the same as what's in the numerator, 0.95. And this probability that I test negative given that I have the infection is going to be 1 minus the probability of testing positive given that you have the infection, which is 1 minus 0.92. This, remember, is our sensitivity, so that's 0.08, 0.08. And this here is the prevalence in the population, that's 0.05. So if you do all that, you get a number pretty close to 1.996. Okay, so under this particular setup, if you test negative, you can be pretty sure you don't have it. If you test positive, you're not terribly sure. You could get a second test, and an interesting exercise is to ask, if you test positive twice, what is your probability of infection? Okay, let's do an example where we use Bayes' rule, but I guess not the baby version. So so this could be some kind of game where there are K bags of marbles. So I don't know. Here's the first one, the second one, all the way up to K of them, and they have marbles in them. And in the first bag, there's just one red marble. In the second bag, there are 2 red marbles. And by the time you get to the Kth bag, all the marbles are red. So there are K marbles in each bag. And so what we're going to do is select a bag at random and draw a marble from it. And we want to know, what is the probability of drawing a red marble? Okay. So for number 1, we're actually not going to be using Bayes' rule. We're just going to be using the law of total probability. So let's let R be the event that we draw a red marble, and let's let B little k be the event that we draw from bag little k. So for number 1, I want to compute the probability of drawing a red marble. So how do I do it? I mean, first I have to choose a bag, and So like I could draw a red marble from this bag or from this bag or all the way from this bag. And so what I can do is add up the different ways, the different disjoint ways in which I could draw a red marble. So we can look at these events BK as a partition um, of the sample space of this experiment. So they're mutually exclusive, and one of them has to happen because I'm going to draw from one of the bags. So now, in order to compute this, what I can do is rewrite this sum, which, let me make a note, this here is just using the law of total probability. I can rewrite each event in that sum as a conditional probability times an unconditional probability. This is a super useful trick. It's not really a trick, it's a super useful fact that we use. I can always write an intersection probability as the product of a conditional and an unconditional. We do this all the time. And so now it's very easy for me to compute this because this first one, given that I draw from bag little k, I know that it has little k over capital K probability of drawing a red marble because little k of the marbles are red out of capital K marbles. And this probability that I draw from that particular bag is just going to be 1 over k because I'm going to select a bag at random such that each bag is equally likely to be chosen. And so now I just need to take the sum. So I have k squared outside, and then the sum little k going from 1 up to k of little k. So here it's helpful to know the sum of the first so many integers. It's k plus 1 over 2. That's what you get from that sum. And yeah, so we get k plus 1 over k with 2k on the bottom. Okay. So that's number 1. Let's look at number 2 where we could use Bayes' rule. Let's say I played this game where, or maybe you played this game and you show me that you drew a red marble, and I want to know what is the probability you drew from a certain bag, from bag little k. So now this is like, what's the probability you drew from bag k given that you got a red marble? If you got a red marble, it's like most likely that you drew from this bag because it's full of red marbles, and it's least likely that you drew from this bag. But how do we compute those probabilities? We can use Bayes' rule. So in the numerator, I'm going to flip the conditionality. This just stands in for my intersection probability. And then in the bottom, I've got probability of drawing a red marble at all. And we can write that with this expression. We've already computed it in part 1. So let me just put it in here. Okay. So like this is just probability of R. Probability of drawing a red marble at all. And so we get, in the denominator, it's this k plus 1 over 2k that we computed from the first part. And in the numerator, it's going to be probability of a red ball from bag little k, which is little k over big K. And then probability of choosing bag k, which is 1 over k. And so I just need to simplify this, and I'm going to wind up with 2k 2 times little k, k plus 1. Okay, good. So that's just kind of a silly example of how we can use Bayes' rule. Okay, so let's move on to the idea of independence. Two events, A and B, are called independent if the following is true. If the probability of their intersection is the product of their probabilities, their unconditional probabilities. Independence in words means the occurrence of one does not affect the probability that the other occurs. So the event A is unaffected by whether the event B happens. So they're kind of not influencing each other. The occurrence of one doesn't influence the occurrence of the other. You can show that if A and B have this property, then the pairs of events A and B complement, A complement B complement, I think I meant to write A complement B, and A complement B complement, all these pairs of events are also independent. To get a better understanding of independence, let me come down here. This is how we usually define independence, but it's equivalent to make this statement or this statement. And I think these two statements are a little easier to grasp. They communicate the idea behind independence a little better, I think. So let's show that these statements are implied by the first one. So if probability of A intersect B is equal to probability of A times probability of B, then the probability of A given B, which is probability of A intersect B over probability of B, is just probability of A times probability of B over probability of B, which is then just probability of A. So I've shown that 1 implies 2. And you can go through and you can show that that 2 implies 3 and then 3 implies 1, so that you get equivalents of all of them. But I won't go through all those details. What does this mean? It means that the probability of A is the same whether B happens or not. So so the prob of A is the same whether B occurs or not. That's what this means, because the conditional probability of A given B is the same as just the probability of A. And also the probability of B is the same as probability of B given A. So the occurrence of one event does not affect the occurrence of the other. That's what we mean by independence. Okay. So let's play a little bit with independence. Let's see, here's just a few properties we might be interested in establishing. I'm just going to go through the first one. So this is just like a result we can show using the definition of independence. It says if the intersection probability is 0 and the probability of A is equal to 1, these together imply that the probability of B is 0. So you might have some that are have this flavor on your homework. So let's look at how we might show something like this. So these two things imply this. Well, we can start by writing probability of A union B equals probability of A plus probability of B minus probability of A intersect B. So that's our one of the things we proved early on. Now, if this is 0 and this is 1, it means what? It means probability of A union B is equal to 1 plus probability of B. And I know that since this is a probability, it cannot exceed 1. And so, because I can't have a probability exceeding 1, probability of B must be equal to 0. Okay, so this means probability of B is 0. Okay, so you can, on your own, try to do these next couple ones. Okay, so I want to do sort of interesting exercise that lets us use a few things that we know. We're going to use the law of total probability. We're going to use the definition of conditional probability, and we're going to use the idea of independence. So this is just kind of a fun problem that brings a lot of different pieces together. So let's say I have a sample space, and the outcomes are just the numbers 1 up to n. And let's say I randomly select a subset A and I randomly select a subset B, and I want to know the probability that A is contained inside B. It turns out we can show that the probability is 3/4 raised to the power n, which is a little bit wild that it comes out to something that simple. Here's how we can show it using a lot of different things that we've learned so far. So if I want to compute the probability that A is contained in B, I have sort of like no good way to begin other than considering writing this as a sum of probabilities using the total law of probability. So sometimes for a set, we write its cardinality by putting bars on either side. So this is number elements in the set A. So if I imagine like a way to partition the possibilities here, I can imagine like A being of any cardinality like 0 all the way up to n, and B could have cardinality from 0 all the way up to n. And what I can do then is imagine taking the intersection of this A contained in B with A having cardinality, say, I, and B having cardinality J. And then I could sum these like this. So this takes me through all the possibilities. Because if I imagine any subset A from here, any subset B from there, I can partition all the possibilities by looking at the cardinalities of the sets. Okay. Now let's think about something. Here I have A contained inside of B. Now, if the cardinality of A is larger than the cardinality of B, then A cannot be inside of B. A must contain some extra elements. So I can, I really only need to consider when I is less than or equal to J. So keep only I less than or equal to J. So let me put J on the outside, and then let me put like I going from 0 up to J of this A contained in B. intersect A has cardinality I and B has cardinality J. So now I still am kind of have no idea how to compute this probability and replace it with a number. So let me just remark that this is the law of total probability, total prob. So I'm going to take this intersection probability and write it as a conditional probability. So I'm going to keep my sum here like this, and I'm going to put probability that A is contained in B given that the cardinality of my set A is I and the cardinality of my set B is J, times the probability of, remember I can write an intersection probability as the product of a conditional and an unconditional. So this is like that. Okay, so I'm basically treating this as one event and this as one event, and so I'm choosing to condition on this one, and then I put its unconditional probability here. Now I'm going to copy and paste. Now I'm going to use the fact or the assumption that A and B are independently selected from these outcomes. Okay, so I independently grab a subset for A and B. So this one I can write as probability A has cardinality I times probability B has cardinality J. Because this intersection probability, since A and B are independent, that can be written as the product of probabilities. So here I'm gonna put probability. Sorry, A has cardinality I, B has cardinality J. Okay, now we can sort of work with this if we think about things carefully. Let's consider the probability that my set B has cardinality J. What am I doing when I draw B? I'm just I'm grabbing any subset of this omega, which is 1 through n. So to compute this, it's going to be number of from the counting rule lecture, we can see that this probability is going to be number of subsets of size j divided by number of subsets of any size. I'm just going to say number of subsets of omega. Number of subsets of size j of omega. Or it should be subsets of omega of size j, sorry. Subsets of omega of size j. Okay, let's figure out what this is from our counting rules. To figure out how many subsets there are, what I can imagine is from all n of these, I can go through all subsets by deciding like yes, no, do I include each one or not? So like I could have no, I don't include any of them, in which case I would get the empty set, which is a subset, or I could have yes, I include all of them, and I would get this one, or I could have like any sequence of yes, no, I include it, I don't, and that would give me a new subset of omega. So the total number of subsets is 2 to the power n, because n times I'm going to choose yes or no, I include it in my subset or not. Okay, so there's 2 to the n total subsets of omega. How many subsets of omega are of size j? Well, that's like, in how many ways can I choose j of these? And that's going to be n choose j. In the same way, the probability that my set A has cardinality I is going to be n choose I over 2 to the n. Now I've got to think about this one. What is this? Okay, probability that A is contained in B. I need to do counting again. So this is going to look like for A to be contained in B, I need all of these elements that are in A to be drawn from the elements in J. So number of ways to draw I elements from the J in B divided by ways to draw I elements from omega. And so I'm going to get j choose I for the numerator, and then in the denominator I'm going to get n choose I. So continuing on, I going from 0 up to j. Now I'm just going to write all this stuff down. N choose I, n choose I 2 to the power n choose j 2 to the power n. Bringing these to the outside, I have 1/4 to the power n. Writing my sum again, I equals 0 up to j, 0 up to j. I've got a cancellation here. I've got, I can move this n choose j over here since it doesn't have an I in it, and I've got ji. Okay, so now how do we make, I'll leave that there. How do we make sense of this mess? Because it seems very hopeless from here to show that this is equal to 3/4 to the power n. Whenever we have a sum of like a combination, a choose thing, we should think about the binomial theorem. So the binomial theorem says, binomial theorem, need to write more legibly, binomial theorem says a plus b to the power n is equal to n choose I, a to the I, b to the n minus I, sum going from 0 up to n. Okay, so when I see something like this, I should immediately try to put it into the binomial theorem. I can put here like 1 to the I, 1 to the j minus I, so I can just add that. It doesn't change anything. And then I see that this whole thing must be 1 plus 1 to the power j by the binomial theorem. So now I've got this, n choose j, 2 to the j. All of this just became 2 to the j. And now here I can again add 1 raised to the power n minus j without changing anything. And then this whole thing is like 2 plus 1 to the power n. And so that's how I get 3/4 to the power n, because this is 3 to the power n. So pretty interesting. I recommend trying to go through and trying to understand all the steps of this one. Even though it seems kind of tedious and weird, it uses a lot of nice concepts. It uses the concepts in a nice way. Okay, so that's how we get 3/4 raised to the power n. All right, so a little bit more I want to cover before wrapping up this lecture. There's a rule we have called the multiplication rule. For any events whatsoever in our sigma algebra, I can compute the probability of their intersection in this way. So remember, we had that inclusion-exclusion formula for computing union probabilities. Intersection ones obey this. So we can prove this result using induction. Let's do that now. Okay, so let me copy an image of this. Copy, paste. All right, I want to prove this. So prove by induction. To prove by induction, because what I'm saying is this holds for every n. So the claim is that for all n greater than or equal to 2, this is true. So we're going to first look at the n equals 2 case, and that's our first step. And then we're going to need to show that case n implies case n plus 1. And that's how proof by induction works. So for n equals 2, I have just a1 intersect a2 is probability of a1 times probability of a2 given a1. So this is true by the definition of conditional probability. So we don't have any work to do here. This we already know. So I can write an intersection probability as a conditional times an unconditional. So we already saw this. So now I want to show that if this is true, then this implies that the statement will be true for n plus 1. So let me begin by writing n plus 1. Okay, so this n plus 1 I can write as, let me put I1 to n and intersect this one. And then I can say this is like probability. So I'm just going to use this case, the n equals 2 case, to say that this probability is given by the product of the probability of this intersection times an plus 1 given probability of this intersection. Okay, and this part, since I can use this n case, this is given by probability a1 times probability a2 given a1, and so on, all the way out to probability an given intersection of all of these. Okay, so that's this, and then I've got coming here probability of an plus 1 given intersection of these I1 to n coming from here. And so this is the n plus 1 case. So so we are done with the proof. So let's say we wanted to use this multiplication rule instead of using counting to get the probability of drawing this poker hand. First of all, let's compute the probability of drawing these in sequence. So the probability of drawing the 10 would be 1 out of 52. Then the probability of drawing the jack, given that you've drawn the 10, would be 1 out of the 51 remaining cards. Then the probability of drawing the queen, given that you've drawn the 10 and the jack, would be 1 out of 50. The probability of drawing the king, given that you've drawn the 10, the jack, and the queen, would be 1 out of 49. And then probability of the ace, given that you've drawn these other cards, is going to be 1 out of 48. And so probability of drawing them in this order would be the product of these. So it's going to be 1 over 52 times 51 on down to 48, which we could write as 52, and then up here I could do 52 minus 5 factorial. But if I want the probability of this hand, I have to consider all the different orderings. So probability of this hand would be 5 factorial times this probability of getting it in any given order. So 52 minus 5 factorial over 52 factorial, we see that that's 1 out of 52 choose 5. And that's what we would have computed by counting, because we would say if this is one unique hand and there are this many possible 5-card hands. Okay, last thing to talk about is an extension of the idea of independence to more than 2 events. So we say that A and B are independent if probability of A intersect B is the product of those probabilities. But if we're dealing with more than 2 events, we have to think about what independence means for a collection of events. So we have 2 different definitions. Mutual independence of a collection of events means for any sub-collection, so any subset of these events, if I compute the probability of their intersection, I get the product of the probabilities. A weaker version of independence among a bunch of events is pairwise independence. That means for every 2, any 2 events I have will satisfy the definition of independence for 2 events. So for all I not equal to j, I have the probability of the intersection of ai and aj is equal to the product of their probabilities. So the reason I said this one is weaker was that mutual independence implies pairwise independence, but pairwise independence does not imply mutual independence. If you're interested in an example, you can look in the textbook at this one. So how might we use this? Let's consider the probability of rolling 3 6s in 8 rolls of a die. We could do this by counting rules, but we could also use the idea of mutual independent rolls of a die. So let's say A1, A2 through A8 are the events such that AI is that you roll a 6 on roll I. Then we might consider, like, let's assume that A1 through A8 are mutually independent. Then we might consider, like, any particular sequence of rolling 6s and non-6s. a6, a7, a8. So let's see, if I roll a 6 3 times, that's what I'm interested in, then it means I roll not a 6 the other 5 times. So these 3 times I'm rolling a 6, let's say. I would compute the probability of this as just the product of the probabilities. So probability A1, probability A2 complement times probability A3 complement times probability A4 times probability A5 complement times probability A6 complement times probability A7 complement times probability of A8. And so for each one of these, I have probability AI is equal to 1 out of 6. And so I see that I get 1 out of 6 to the power 3 because I have 3, there's 3 times that I'm rolling a 6, and then I have 5 out of 6, that's the probability of each complement, raised to the power 5. Now I would need to consider all the different ways in which I could choose 3 of these events to happen instead of the complement happening. So probability of rolling 3 6s in 8 rolls would be 8 choose 3 times that probability. Now, a way to get to the same thing by counting would be to say that this probability is just the ratio of 2 things. So there's number of ways to roll 8 times, and then there's in the numerator number of ways to roll 3 6s out of the 8 times. And so in the denominator, how many sequences of rolls could we have? There's 6 possibilities to the power 8, so it's like I'm sampling from 1 through 6 with replacement 8 times. And then ways to roll 3 6s. I've got I'm going to there's okay, I'm going to roll 8 times, and I need to choose which 3 of those 8 are going to be my 6s. And then once I do that, I still need to choose. I need to count what comes up on the rest of the rolls. And so I have 5 rolls left, and for each of those 5 rolls, I have 5 possibilities because they can't be 6s again. So that's 5 to the power 5. And if I just write that in a different way, I see that it's 5 out of 6 to the power 5, 1 out of 6 to the power 3. So I get the same thing. Okay, we are done with this lecture.